Okay, ladies and gentlemen, let's begin. We're going to talk about solving equations today. Hopefully that was made clear from your warm-up today too. Thanks, guys. So the warm-up is a good kind of preamble to what we're about to talk about today. We're going to solve equations, and you've already just showed me that you can solve some simple equations of this kind, and this is going to be absolutely prerequisite for what we're about to do. We're going to solve equations that are a little more complicated, like this first one. Well, actually, no, that's not what it says.
No,
it says prove or disprove, which I told you was maybe coming. We've been proving identities, and I said, some of you have asked, like, well, what happens if they're not true? Well, we won't ever say, no mathematician would ever ask you to prove something if they intentionally knew it wasn't true. But we might say something like prove or disprove. So do stare at this for a second and ask yourself, is this an identity or is it a conditional equation? And by that I mean the things we've been doing, like all these ones that are over here on the board. This statement here, for instance, number 47 from the homework. Do you understand what an identity really means? It means that if you plug an x value in on this side, you get the same thing no matter what that x value is, as if you plug it in on the right side. Or if you were to graph the left side in y1 and you were to graph the right side in y2, you would get the same graph, right? And for every x value for which the expression on the left is defined, it equals the expression when evaluated on the right side for that value, right? So that's what an identity means. It works for all x. So that's the question. Does this one work for all x? Or does it work for maybe just some x, right? In which case, that's kind of like the normal equations we might encounter in life. What's your hunch? Have you looked at it a couple seconds here now? What do you think?
Oh, okay. Yeah, I got it.
Judah has a hunch.
It only works with 2 cosine x equals 1.
All right, so you're noticing this. There's like some structure here you're noticing. You're noticing that, like, hey, there's a sine squared here. And in order for this to be true, it must be true that 2 cosine x is just equal to 1. He's noticing there's a sine squared on both sides. Do you hear what he's saying? All right, and then, so keep going. So what's your hunch?
So x over 2 and cosine x equals 1/2, which means that x is...
All right, well, the point is 2 cosine x equals 1. That's not always true, and that's pretty clear in your mind. And we will solve that in a second, yeah, for sure. So how do you disprove that this is true for all x values? Yeah.
Show counterexample.
Yeah, that's the key word here. You show one counterexample. Okay, so give me an x value that does not satisfy this equation. Can you do it? Just maybe take a guess and see. Well, something maybe we can actually evaluate without a calculator. Pi over 3.
No, but that's the one that works.
I think pi over 3 might be a bad example. except the fact that, like, if you guess wrong, pi over 3 actually does work. Which means you've actually accidentally stumbled on one of the answers, which we're gonna do in a second here. So that's cool, right?
That's sort of lucky.
That's kind of lucky, actually. We could consider it lucky or unlucky, I don't know which.
So pi over 6.
Pi over 6 you want to do?
Yeah.
All right, let's try pi over 6. So let x equal pi over 6. Then the left-hand side is equal to, help me out here, sine of pi over 6 is not all at once.
That's a half.
Yeah, it's 1/2, and then we're going to square it. And then cosine of pi over 6 is root 3 over 2. So and then in the end we get what? Root 3 over 8. All right, and on the right-hand side, we have 1/2 squared, which is 1/4.
But you need to multiply by the 2 on the with the root 3
Oh, yeah,
over
yeah.
8, you didn't multiply by the 2.
Oh, yeah, you're right. So 16 down there.
Boom.
All right. So the point is, these are not equal. So pi over 6 provides a counterexample.
Wouldn't it be 2?
Oh, don't criticize my math. No, it's probably. Is there something else wrong?
Root 3 over 4. Wouldn't it be root 3 over 4?
Whoa. Hold up, everybody.
Wouldn't it be root 3 over 4? Because you're multiplying by 2, so you put that on the top, and you get rid of the 8, and it becomes root 3 over 4.
Oh, yeah, you're right.
Man, 2 times.
Man, in a row. I was just so excited to get to the rest of this problem, and I just didn't care. What do I have to do if I get something wrong?
Mr. Getz during the summer did if you did 3 mistakes in one class period, you have to do a stupid human turn.
Oh, okay.
Like one hand.
All right, I'm good for that. You know I'm good for that. If I make 3 mistakes in a period, I have to do a stupid human trick. I'm good for that. That's for sure. Okay. Well, I guess you'll find out if I make one mistake. All right. Here we go. So I think I'm ready to actually solve this now. We've already kind of stumbled upon a solution, at least, thanks to Adele. So what should I do? I mean, now let's treat this as an equation, a conditional equation like we've done before, and let's just start working with it. What do you think we can do? Anything we can do? What strikes you, Maddie?
If either sine squared x or cosine x equals 0.
Okay, if sine squared x equals 0, I think you're right, we have a solution. If cosine x equals 0, I'm not so sure.
No, because,
Yeah.
Well, you could just make sine of yourself. You can get it down to cosine x equals.
Okay, I mean, I hear some thoughts. Keep sharing. Go ahead, Rafi. Yeah, I mean, this is kind of, I think this is coming out here,
Yeah.
right? The one thing I want to caution you against is, and this is kind of like, I want to say this to people who might think that, oh, this is only true when 2 cosine x equals 1. I think the thought you're having is that you can divide both sides by sine squared. You just have to be careful with that. Because you know, like back in the day in algebra, if you're like in algebra 1,
Plus or minus.
you might have made this mistake. Oh, we can divide both sides by x. And then we get x equals 1. Well, yeah, but you're missing a solution, aren't you? Right? What should you have done? Okay, keep that in mind. No. You should have, right? You should have, yeah, you know?
Oh, you
Okay? You should have done this. Which is what Rafi is saying. And then what?
But then
What's
you
the word? Yeah, factor, right? Like that's what the person over here needs to learn that lesson, and that's what we're gonna do here too.
But for this one, it does work dividing sine squared to
No,
x, right?
no.
No?
I'm suggesting that you'll lose a solution. All right, so what are our solutions? Just like you lost the solution over there, you're gonna lose the solution here if you ignore the sign x,
Yeah,
right?
you assume
Oh,
that sine x.
you don't get 0.
You assume that sine x when sine squared x is not 0.
All right, so do you understand why we did the warm-up today? Now at this juncture, we had a complicated equation we started with, and now we have 2 little equations of the type we did in the warm-up today. We're solving on the domain 0 to 2 pi, the half open interval. So here we get x equals, in fact, that's one of the problems we did, 0 or pi. And over here we get
X equals
pi over 3 or
5 pi over
5 pi over 3, yeah.
3. So really you'd be losing 2 answers.
Yes, you would lose 2 answers. You'd actually lose the 0 and the pi solutions if you ignored the sign, wouldn't you? Feel free to justify, go back and just plug any one of these 4 solutions back in and you'll get a true statement, okay? So, you see how this works? You like it?
How'd you go from sine 2x to sine x?
Oh, you take out the sine x.
I factored out a sine squared.
I see.
All right. So, moving along. Here we go.
I like beta.
You like beta?
Can we go back to like 5 seconds?
No, but how about 2 seconds? 1,
Okay.
2. Okay. You like that deal we struck? That was a good deal. All right. Next slide.
Let me try this.
Okay, so what strikes you? I mean, we'll just go. There are lots of ways to maybe think about getting into a solution on this. What do you want to do?
Subtracting sine beta minus cosine beta. Like
Subtract
subtracting the
something?
tangent.
All right, yeah, we could subtract off the tangent on both sides. That's
Then you can factor.
fine.
Yeah, this one's really easy.
All right, what next?
So then just change it to sine and cosine.
Okay, okay. So we have sine.
Beta over cosine beta.
All right. What next? What do you want to do?
Or you can subtract them, yeah. Yeah.
Yeah, make it one fraction.
I mean, ultimately we want to factor this, right?
It's convenient to me.
So, I mean,
But it's convenient to make it one fraction because
Yeah,
then you
then
can
you just
factor
factor the
easily.
top.
Then you just factor out the top that you get.
can I factor a sine over cosine out?
Oh, you get sine squared beta over cosine beta. That's actually 17.
Do you like that?
Dang. That's
that okay?
awesome.
Great. Okay, and then we have that sine beta is equal to 0.
Wait, where do we get sine?
I mean, sine over cosine is equal to 0.
Oh.
Or, no, it's the same thing. I'm just saying sine beta over cosine beta equals 0. The only time that's true is when sine beta equals 0. So I'm just quickening our work by just saying, isn't this only true? This is 0 only if sine beta is 0. And over here, we have sine squared beta equals 1. How are we doing? We've solved this one a couple times today. Beta equals
Pi and 0.
0 and pi. And over here we have, what's going on there? Sine squared beta equals 1. So, help me out.
Take the square root.
Sine beta equals.
So sine beta equals,
Sine beta equals 1.
sine beta equals 1.
Yeah.
Or negative 1. All right, so when is that true?
Pi over negative pi.
Pi over 2 or 3 pi over 2?
Yeah, you can't go to negatives because
Okay, so yeah, we're on this interval, remember. So then, are we good? Are we satisfied with how that felt? Except, Eric, speak up again. Yeah, we can't have that cosine beta be 0. And is that a problem here? Is something?
So 0 can't be an answer, right?
Well, I mean, try these in the original equation.
Yeah, because beta can't equal 0 at all. So
Well,
0
careful.
doesn't work.
When is cosine? We have a problem. I agree. When cosine beta is 0. So what beta? Careful. We're not thinking about beta. We're thinking about cosine beta. So what beta would make cosine beta 0? Try both of those solutions. They do work. Try either of the other ones, and they don't work. Try it, right? In fact, they make both sides undefined,
Oh, because beta,
right? Tangent is undefined at pi over 2 and 3 pi over 2. So,
because that would make cosine 1.
and it makes cosine. Yeah, these make cosine 1, so they're okay. All right. So that introduction there was the algebras may be interesting, but the main thing I want to highlight on this particular problem is the fact that, like, on these problems as we're solving, we need to be super aware that extraneous solutions are going to be lurking. Okay. Just that's my message to you. It makes the original expressions on both sides undefined. Pi over 2 and 3 pi over 2. Cosine of pi over 2 is 0. That's a problem, isn't it, for the original expression on the left?
I see.
Yeah.
Once we walk in tomorrow, it's like,
All right, next. Focus. All right. So, again, I mean, the algebra is interesting here.
Oh, this one's actually not that bad.
That's not the thing I want to highlight here. The solving is, I don't know, maybe we change that into sine over cosine. Cosi. Sine and cosi. Okay. Sine and cosi. All right, and then let's go on over here. Well, we can divide by this. We can also multiply by its reciprocal. Do you see that we get 2 cosine squared then on the left? Like I said, hopefully the algebra is okay here. And I'm like doing it all for you, but that's okay. But this is not the interesting part for me on this problem. I want to say something else here. So we get cosine y
Oh, that's
equals
where I messed up.
0, and we get cosine y equals cosine coi. All right, so on the left, cosine y equals 0 when? We just talked about that.
0 pi.
0 in pi? No.
No, pi over 2 and 3 pi over 2.
Pi over 2 and 3 pi over 2. But Judah, I hear saying off to the side that we didn't even have to have that conversation because,
Yeah, it doesn't.
yeah, because cosine y is definitely not allowed to be 0, right?
Yeah.
try that in the original equation. If you learned anything from the last problem, it's that. Okay. But over here, can cosine y equal 1? Sure. And when does that happen?
I am 0.
Or I'm sorry, 1/2.
Oh. Hey, that's 3.
Okay, you ready? Okay, here's my superhuman trick. Would you like? I'm gonna poke my entire head through through a hole this big. Are you ready? Am I doing it? I'm poking my head through a hole this big.
Not your entire head.
Yeah, only that one small point on your forehead.
Oh, okay. There you go. That was my stupid human trick. All right. Poke your head through a hole this big. It's easy. It's easy. You can do this at home. Okay. All right.
I finally do something Mr. Chase can do also.
So did we ever figure out what that answer is? We've done this one a couple times today. It's pi over 3 and 5 pi over 3.
Yeah.
All right, like I said, that's actually not the interesting part of this problem. The one thing I want to layer on top of this problem that you didn't notice is the instructions, which say not solve on a certain interval, but for all y. So this is just 2 of an infinite number of other possible solutions. And how do we describe them? Well, we've kind of talked about this before, but a good way to write those solutions is pi over 3, or we might say, or anything coterminal to pi over 3 will also have a cosine of 1/2, right? So how about pi over 3 plus 2 pi n, we might write, where n is some integer,
Can we write
either
X
positive or
or Y
negative. Huh?
Oh, we can't write Y.
Well, if I let n be an integer, then I'm supposing that n could be, you could let n be -5 or something.
Oh, we can't use I.
Well, no, because if you only add 180 degrees, then you get 4 pi over 3, not 5 pi over 3. And that solution is that answer is not that value is not a solution. So we also have 5 pi over 3 plus anything coterminal to that, right? Plus 2 pi n, where n is an integer, right?
Oh.
And by integer we mean positive or negative whole number, right? So we're okay.
Wait, how do you write that? What's that last thing?
This is a z. It's a double struck z, right? This means integers. It's from German, actually. It's from the German.
I never learned that.
Okay. So cool. Do we have any German people in here? No. Okay. No one speaks German. I'm gonna butcher the German, but I think it's Zählen is counting in German. It's like the counting numbers. The way you call the counting numbers, like 1, 2, 3 in German, are Zählen. Zählen. Yeah. Like this. All right. Another, if you want to, that's full credit for that. If you want cool points, listen to what I'm about to say. You could get some cool points for this, okay? Notice that another way to write this, you could put right here any angle coterminal to this plus 2 pi n, right? So we could say negative pi over 3 is another good place to start there, plus 2 pi n. That would describe this section of solutions equally. So another really nice way to write this would be, how about plus or minus pi over 3 plus 2 pi n, right? Would be like a, right? That'd be a cool.
But you still have to write the plus one.
That'd be a cool way to write this if you want to. It's supposed to be sunglasses.
Is that going
All
to
right.
work for all equations?
No.
So we only got one there.
No, I just wanted to, so you could write it a little more
So we got
compactly.
one.
Yeah. Oh yeah, sorry Peter, what? Shh, guys don't want to hear Peter. Sine y is, wait, what? Alright. Okay, let's try another one.
What is sine u?
Factor out a sine u, I hear you say. Sounds great, let's do it.
Does it say solve for all these? No, you don't have to bring it up first. It'll make it easier to know you can.
Yeah, that's true.
So again, I mean, the solution set is the thing I'm interested in thinking about here. The solving is not the interesting part. There, neat. All right. So u equals 0 or pi, and over here, u equals pi over something. Pi over something.
Oh, there was a -1.
So yeah, pi over 4 and 5 pi over 4 both have a tangent of 1. But again, we're finding all values, so how do we write that? Well, one way would be to write u equals 0 plus 2 pi n, or u equals pi plus 2 pi n. I'm a mindless zombie. Pi over 4 plus 2 pi n, or u equals 5 pi over 4.
Wait, so you'd have to write all of
Write those in the citation and just have like basically like
Where n is an integer. Okay.
So we'd have to do this for all
So you could do that, but there is a little bit of a slicker way to write these. You could just write, think about what you're actually saying here. You're saying 0 or pi or 2 pi or 3 pi or 4 pi or 5 pi or negative 27 pi or any, what would be another way to write these first two statements compactly? Just the first two statements. Yeah, how about just, what'd you say? Pi n, right? Would be a great way to just write that first set. That combines those two nicely in a slick, again, cool points, cool points. The second two can be combined nicely too if we remember that tangent,
Oh, you could do it.
what's happening there? Pi over 4 and then 5 pi over 4 in the air. I'm doing it with my hands here. Pi over 4, 5. This angle and then 180 degrees later.
Yeah, you could do plus or minus pi over 4.
I don't like plus or minus pi over 4 because that insinuates that you can get this as a solution. That's not right. Yeah, and why does plus pi n, why does repeating solutions every pi make sense? In fact, this will always happen with tangent. Why?
Oh, because tangent's period is only
Because tangent's period is pi, right? Right? So it makes sense that that's happening here. So you could combine the next two really nicely by saying pi over 4 plus pi n. And you'll always kind of have that happening with tangent. All right. So this describes very nicely the set of solutions right there too. Again, just cool points. You don't have to do that. If I talk about that, you'll know what I mean though. Okay.
Wait, so on a test before it, will you be like, there are cool points involved with this one?
No, not necessarily.
You should say that before a test. So you know that.
I would give, if I were allowed in Montgomery County to give you bonus points, I would. I totally would. I like one. I like the idea of All right. Cosine x equals something. What do I do? Algebra. Cosine squared x equals a 4. So what are we looking at here? So cosine x equals positive half. I've already solved a couple times today, right? That's pi over 3 and 5 pi over 3 both have a cosine of positive.
Why does this keep happening?
Positive a half. Also, if cosine x is negative a half, that means x is either 2 pi over 3 or 4 pi over 3. And again, there's some serious cool points available for you on this one, okay? Pi over 3, like just think about it in the air with me. Pi over 3 looks like this. 5 pi over 3 looks like this. 2 pi over 3 looks like this. So I could pick up pi over 3.
Oh.
I've got all these here, right? All
Never
4 of
seen
these.
one.
So how about we just write, are you ready for this? How about we just write x equals plus or minus pi over 3 plus pi n.
So we got lucky.
You like that way of writing it? Again, this is all about cool points right now. Okay? What's that? So that means what I'm writing here is, if you think of pi over 3, I'm picking up pi over 3, then 4 pi over 3. And then everything, all those guys in the air here. And then I'm also picking up negative pi over 3 and everything 180 degrees off from those, right? All right, so just want to make sure you understand why I'm writing what I'm writing. Let's do another one. This looks like fun. Do you like all the examples? We're doing so many examples. Don't want you to give us a prize. Where are you? I made my day. Okay, yeah. I love a good pun. Okay. Cosine squared. We got. Oh, this looks nasty. What's going on here? We can.
Oh, we can completely factor?
We can factor this maybe, right? No big deal if we can't factor. Maybe we could use the quadratic formula or something, right? That'd be all right too. So
We're using
whatever.
quadratic formula.
But if Mr. Chase was nice, maybe it factors. I don't know. Let's see.
Oh, it does, yeah.
Does that work?
Oh, it's not 10.
Yeah, 10 and 1 add up to 11. That works.
10
Okay.
and 1 add up to 11, but you needed the 2 in the front, buddy.
So that's kind of fun.
How was I wrong?
This is our favorite problem today.
Why? Why does this happen? We've had that.
All right, I'm having trouble with the other one though. Cosine theta equals -5. When theta equals. Talk to me about this second piece here. Talk to me about this second piece here. I need some help. Talk to me about the second piece. Where are you? Where are you? Hello? Hello? Is this thing on? Okay. Talk to me about the second piece.
It's some radiant
Yeah, maybe we need to get out. We need to get our calculator out and do inverse cosine to -5. Maybe it's possible these come out to be not nice numbers, right?
Do we actually have to get a calculator?
No.
Oh, it's not gonna.
Come on, people.
Oh, wait, it's not.
Everyone point and laugh at the people who took out their calculators.
Wait. So that would be. Oh. So that would be.
What?
-5 would be like if it's -1.
What's going on here? Somebody say it.
Does it work?
Can cosine be -5 ever? No. All right.
Oh, but it said from. Okay.
Yeah, that time we were only solving on that one interval, right?
But it could have worked if it was. If it was in another interval, could it have worked?
I mean, yeah, we could. No, I mean that cosine of theta will never be -5. Ever.
Oh, okay, got you.
Next problem. All right. Sine squared. This looks equally exciting, but I'm a little stymied at the beginning. Let's just wait in silence until someone has an epiphany. Ready? Just do that. Just have an epiphany. Go.
Got it.
I have a thing.
No, you put the.
Did I hear Eureka?
Eureka.
What can you do? I mean, last time we liked that one last time because it's quadratic and cosine. This has got like stuff going on. I don't know what's going on. You ready for Judah to give the spoiler? Or no, I don't want to. Lise, you want to give the spoiler? We haven't heard from you yet. Go. What do you think?
If you subtract 1 from both sides, you have 2 sine squared what is that? What's that?
Oh, phi or phi.
Okay. So you have 2 sine squared phi plus 2 squared minus 1 equals 0. Phi, and then and then if you put 2 sine squared phi minus 1 plus cosine phi, then 2 sine squared phi minus 1 simplifies to 2 cosine squared. What? Okay.
I think you said, yeah, I think about what you just said.
Subtract one.
And that's my thought.
Plus cosine.
Yeah.
I like the idea of having the sine squared disappear, that's for sure.
Oh, I just made it.
Oh, wait, no, there's
Can I play into it?
What do you see? Huh? I'm not sure I hear you on that. Reem?
Basketball fans, don't forget to attend the boys' game tonight at 7:15 as they take on Blair. Also, everyone is invited to attend the annual Winter Instrumental Showcase.
Right?
At 7 p.m. in the auditorium.
You like Reem's move?
Our students and
Are we good? I mean, let's move on now, right? Here we go.
Oh, I did it different.
Now it's quadratic and cosine. That's beautiful, right? So let's do stuff. Cosine squared. Plus minus 2. Is that minus 1 equals 0? Check my algebra. Check my algebra. I also changed the sign on everything. Just because.
Wait, negative? Wouldn't it be, isn't it positive?
Oh, because you, yeah, no, I know why. No, it's not.
Oh, we flipped all the signs. Last one.
I'm hoping this works. I don't know. What do we need? A minus and a plus?
I thought this
1?
was like interesting.
Hey, it's our favorite problem again. Cosine 5 equals negative a half.
Do you have it so it automatically has a
No. The teacher, of course, he picked the problem.
Pi over 2 pi over 3.
That would be odd. If they did a test
4
like
pi.
that, and it just somehow always ended up the same.
That'd be great.
One's cosine 1.
What? I know, that would be great. And yeah, they set it up like that.
Alright, I guess that's the end. More examples, more fun.